So it's the next speaker is Lorenzo Tamellini. He's a senior researcher at the CNR IMATE in Pavia. And yeah, it's our pleasure that you could accept this invitation, and you can just proceed with your presentation of your research.
Okay, great. Thanks, Joachim, for setting up the stage. Thanks, everyone, for listening. It's too bad I cannot be there, hopefully next year. But in the meantime, can you hear me well and can you see my screen?
Yes.
Okay. How much time do I have? 45 minutes or so?
You have 1 hour, but that includes questions.
Yes, including questions. So, okay, great. So the title of my talk is, as you see on the screen, data-informed UQ for laser-based power bed fusion additive manufacturing by multi-fidelity surrogate modeling. There's a lot to unpack here. So I will, let's see how well I can do. The outline of the talk, first I will give you a brief introduction to the so-called multi-index stochastic allocation. I don't think that this is really, most of you are very familiar with this anyway, but just in case someone in the audience is not experienced with that, that's a special multi-fidelity method for parametric PDEs. It extends the sparse critical allocation method, and what you get at the end of the day, this is a surrogate modeling approach. So you get a response surface of the quantity of interest of your problem that you can use for the quantification purposes. And then I will spend most of my time talking about the additive manufacturing problem that we try to tackle with the multi-index stochastic allocation method. So I have to acknowledge a bunch of people. As for the multi-index stochastic allocation, several people have worked on that during the years. So Raul and Fabio and Abdul Latif and Joachim, all in the room as far as I know, and Chiara Piazzola also. She was a postdoc with me in Pavia, and now she is at Munich TUM. And regarding the application today at the additive manufacturing problem, the group of civil engineering at University of Pavia, so Ferdinando Ricchio, Massimo Carraturo, Michaela Chiappetta, and Alessandro Reali, and then again Chiara Piazzola. So first part is where I talk to you about multi-index stochastic allocation. So if you are already familiar with this, just feel free to check your email for 5 minutes. I'll tell you when I'm done with this. Those of you who don't know, this is a brief introduction to the method. So throughout the talk, I'm interested in computing a quantity of interest F out of a PDE. This quantity of interest F depends on n uncertain parameters. The PDE that we are working with depends on n uncertain parameters. I call the parameters Z1 to Zn, and F is the output of the PDE solver. For instance, just to fix ideas, in the final application, the quantity of interest will be the warpage of the component that I'm printing, and as well as the strains. So quantity of interest that are deduced from the solution of the PDE. The PDE solver, we assume it depends on R hyperparameters. By hyperparameters, I mean mesh sizes, time steps, tolerances for solvers, these sort of things. So parameters are physical quantities. Hyperparameters are my knobs to decide what solver I'm actually using. And then I collect in a vector alpha that has R components. It's a multi-index that I use to control the PDE hyperparameter. So for instance, the mesh size could be 2 power minus alpha. or the time step could be 2 minus alpha, or maybe I want to play both with the mesh size and time step, and then I have two components, and then H will be 2 power minus alpha 1, and delta T will be 2 power minus alpha 2. Same thing for beta. Beta is a multi-index. It has n component, and each component of beta controls how much I sample the parameter space along the each parameter. So for instance, I could decide that I put 2 power beta I minus 1 points along each direction of the parametric space. And then f sub alpha beta is the approximation of the quantity of interest that I'm interested in, given a PD solver with hyperparameters alpha, controlled by alpha, and sampling scheme controlled by beta. So for instance, here, if I want to solve a linear elasticity problem over this banana shape, and imagining that the elastic equation depends on two uncertain parameters, this here is a picturesque representation of the fact that I want to use a multi-index 2, 4, 2 to decide the three discretizations of the mesh. So you see here it's the mesh is 4 by 16 by 4, so multi-index 2, 4, 2, and I'm using 3 times 9 points in the collocation space. So a multi-index 2 and 4, 2 for 3 points, and 4 multi-index 4 gives me 9 points. And then I collect. I want to juggle not just one discretization f sub alpha beta. I want to juggle multiple approximations. So I need to collect all the approximations indexed by alpha beta in a multi-index set. And then, as I said, as I promised, I want to juggle many approximations. What I mean by this more specifically is the MISC formula gives you this approximation. So the approximation of your quantity of interest, f of z, is the MISC approximation, is a linear combination, as you see here, of multiple approximations, f sub alpha beta, each one multiplied by a certain coefficient, c. The coefficient depends on the alpha beta. So this is what I mean by I'm juggling multiple combinations, multiple approximations. This has advantages if you do things properly, let's say. So just a pictorial representation of MISC. Imagine that you have just one hyperparameter, so r equal 1. Imagine that you have one uncertain parameter, so n equal 1. And imagine that you have two levels of mesh. So you see here on the horizontal axis, I have alpha equal 1, alpha equal 2. On the vertical axis, imagine that I can either, say, compute one with one parameter, 1 point in a parameter space, or 2 points in a parameter space, so 1 and 2. I have these 4 possible f sub alpha beta, C, Q, F, and P, and I'm looking for a certain linear combination of P, C, and Q, and F. And in particular, F is the highest fidelity, so where I compute a lot of samples, where a lot in this scenario is 2, over a fine mesh. This is out of reach, so the MISC approximation takes into account the other 3 possible approximations, P, C, and Q, and I will not tell you exactly why, but the corresponding formula is this. The approximation of the quantity of interest is the approximation P plus the approximation Q minus the approximation P minus the approximation C. So the coefficients C alpha beta are 1, 1, minus 1, and the 3 F sub alpha beta are the P, the Q, and the C. And this, in a nutshell, is MISC. Of course, this is just a cartoon, and in principle, I have more than 2 levels of PDEs or hyperparameters. I have more than 2 choices for the number of samples. So I have more than 4 possible combinations of alpha beta. So I have a larger universe of possible combinations. So I want to choose the best set of approximations to combine, and there's an algorithm to do that. It's a very standard algorithm. It's inspired by the usual Gersten-Griebel a posteriori algorithm for sparse-grids. So it essentially goes around in this space of all possible approximations and computes a profit for each of them, and iteratively selects the most profitable one, and then goes on and on. So it's very easy in a way. Devil's in the details, but overall the idea is quite simple. So in practice, what this method does, it reconstructs a full approximation as a linear combination of many coarser solutions. So you see here, I'm reconstructing the true solution as a linear combination of P and Q and C. So a linear combination of many coarser solutions. It extends the sparse grids approach to a multi-fidelity approach. Sparse grid stochastic allocation will be single fidelity. Instead, here we're playing with multiple fidelities with the hyperparameter alpha. So it's a multi-fidelity method. And if you do things carefully, it balances the solver error, the PDE solver, and the parametric error. We do have convergence rates. These are the convergence rates resembles those of sparse grids. So you don't, I mean, if you know those results, you know what I'm talking about. If you don't know those results, it's enough for you for today that you know that there are convergence rates. And this is completely, let's say, a completely black box approach. So any solver can be used. And at the end of the day, what you get is a list of PDEs to be solved for different values of the parameters. And each of these PDEs is to be solved on one or more meshes that are decided by MISC. So it's really fully legitimate multi-fidelity approach. This is a pictogram of what happens. In this case, you see that I'm juggling, like on the left here, you see that I'm juggling like 20, 25 different F sub alpha beta on the left. On the right, you see the list, the parameter space. Each dot is a PDE to be solved. Each color is a different mesh. And this is the result of MISC, essentially. Then I think I will just skip. This is a standard test case. I don't want to talk about this. This is here just the purpose of showing you that the convergence of MISC is better than the convergence of purely sample-based approaches like multi-level Monte Carlo and multi-index multi-level Monte Carlo, just because I'm using a surrogate model. So whenever a surrogate model is suitable, MISC is better than sampling based approaches. And this is essentially when the response of the PD, so the quantity of interest, depends smoothly on the uncertain parameters. And why is that? Because the idea is that you explore most of the variability of the output with a lot of queries to a coarse solver, and then you correct with only a handful of calls to the higher fidelities. So here, this cartoon here is just to show you that in the previous convergence line that I was showing, you see that eventually here I'm using for the finest fidelity, for the finest tolerance that I'm requesting, I'm evaluating only 100 times the largest mesh, or versus a few thousands evaluations of the coarse mesh. So this is why we gain in complexity, let's say. So now it's time for those who disconnected because they know MISC. It's time to get back to me because now I'm going to talk about the application, the additive manufacturing problem. So let's try and make this informative also on the application. I want to give you some flavor of the actual problem. So this is a 3D printing in practice problem. Specifically, I'm talking about 3D printing of metals. And 3D printing of metals is usually done by this technology that's called laser-based power bed fusion. So there's in 3D printers, it's this machine, there's a layer of powder, a laser goes around and melts the metal. Everything cools down. Another layer of powder is laid. Another time the laser goes around and melts the powder, and in this way, an object is built layer by layer. The issue is that these printers they don't produce exactly the shape that you request due to a number of issues. Surface roughness, I mean, you can imagine that by doing a layer by layer approach, each layer will be felt. There's a surface roughness to it. The laser, you need to be able to control the laser path. So if you are unable to do that, the shape that you get is not the one that you want. Of course, there will be need for support structures, so small, let's say, pedestals or columns that you want to be there just while building, while printing, and then you want to remove them. But when you snap away these support structures, there you might be left with an imperfection in the surface. There are thermal deformations because, of course, here there's a metal that is being constantly heated up and cooled down every time the laser goes by. There are a lot of thermal deformations, and there are residual stresses. And we focus, the problem that I was facing, that we are facing in this talk is what to do with residual stresses. And let me be clear, what do I mean by residual stresses? It means that, let's say you want to print this object here, this beam or this comb if you want. Can you see my mouse, by the way? If I move the mouse? Maybe not. But anyways.
Yes.
Okay. So if you print you want to print the comb, what you do in practice is there's a build plate, a larger chunk of metal, and then you print the beam on top of this. Then you want to remove, of course, the comb, because that's your final object, the thing that you care about. You don't care about the build plate. The moment you cut the red areas to remove the comb from the build plate, there will be an undesired warping. It means this: you cut it open, internal residual stresses are released, and the deformation is applied. It's pretty much like when you crack open a watermelon. Once you crack open the watermelon, you will never be able to put it back together, because the moment you crack it open, internal stresses are released, and these deformations happen. And of course, we don't want the deformed part, we want the original one. So we want to monitor the residual stresses and to optimize the printing process such that the residual stresses are as little as possible. There are thermal treatment, so if you bake the objects before cutting them open, it improves the release of these stresses. But still, ideally, you want to have a FEM self-solver, a FEM simulator that simulates the printing process and predicts the residual stresses. You want to optimize the process to reduce the stresses. Problem is, these simulations are crazy expensive. Like, crazy expensive means you will see what I mean by crazy expensive. It's a matter of days on supercomputers. So what we do, we brutally simplify the physics. We go ballistic. So to begin with, we ignore the scanning path. So instead of having a laser that goes around, if you want to simulate the printing of a whole component, you have to assume that multiple layers are laid immediately and deposited in one go without simulating the scanning path. Then, instead of solving a time-dependent, fully plasto-thermal PDE, what you do is you solve a time-dependent, non-linear thermal equation only on the sequence of geometries that you have. And then you store the thermal field history, and then you solve a quasi-static mechanical problem to evaluate the thermal strains. So a sequence of mechanical problems, but you forget about the temporal evolution. And now the problem is we're replacing a couple of viscoelastoplastic thermal PDE with a thermal PDE and a mechanical PDE. So the physics is totally made up. So what kind of parameters do we want to do we use in this thermal plus linear mechanical? We don't know. Those phenomena don't exist in reality. So we need to cook up the parameters of the non-linear thermal equation and of the quasi-statical mechanical problem to have this super simplified and non-realistic physics, have it match with the real process. And what we do an inverse Bayesian analysis to find the parameters of this cooked up physics that match the experimental results. And we do this by using surrogates, either sparse-grids or MISC. In particular, we have displacement data. We have warp page data. So someone prints the comb, measures the displacements, and with this data, we compute the posterior PDF of the uncertain parameters, and then we propagate the posterior PDF through the model to compute the PDF of the residual stresses. And then we're done. Once we have the residual stresses, we are done. So what we did, or what we do in this talk is we compute a surrogate model, either single fidelity or multi-fidelity, for the displacements of the comb being printed. We do a preliminary round of global sensitivity analysis to drop the useless parameters. Then we refine our surrogate model based on this analysis. We do inverse Bayesian to compute the PDF of the posterior PDF of the uncertain parameters. And then we compute a new surrogate model. Now it's a surrogate model for the strains, not for the displacements, tuned to the posterior to predict the strains. And then we query the surrogate model to compute the PDF of the strains. I will walk you through two test cases. The first test case is with synthetic data, and it uses a single fidelity approach. This is already enough to walk you through most of the technical difficulties. Once I'm done with that, hopefully I will make it also to the second test case, where we actually use this time a multi-fidelity surrogate model with real data provided by NIST, the National Institute of Science and Technology from the US. But I want to give you a spoiler on the results, because maybe you want to see this first. So this is the result. So this is the thing that I'm printing. The x-axis on the right, you have to think that it goes here, this direction. So from this direction of the x-axis, you see here in gray shade. Hopefully you see a gray shade with the prior uncertainty, and then depending on the quality of the beamer there. And then the posterior uncertainty instead is the red pink shade area, very, very much better, much concentrated. The posterior is a unimodal, and the mode of the posterior pretty much coincides with the target value of the synthetic test case. In the second test case, where we have real data, the concentration of the posterior is less evident, but let's say we were happy anyway, because the mode of the posterior, the mode of the prediction of the strains matches fairly well the data that we have from the NIST. So we were happy. Whereas the mode of the quantity of interest with prior PDFs was totally unrelated to the NIST data. So in short, we are using either a single fidelity or a multi-fidelity surrogate for a complicated problem. We are able to predict everything. It works. But there are some technical difficulties. The first difficulty that was mentioned is computational time. One simulation takes 4 hours on the lowest fidelity mesh and 6 days on the high fidelity mesh. And it's not 6 days on my laptop, it's 6 days on the server that were provided by us to us by ANSYS. We are using ANSYS to simulate the 3D printing process. ANSYS gives us servers. One simulation takes 6 days on those servers. So it's really something, let's say. Then we didn't go fully Bayesian, so we didn't go Markov chain Monte Carlo. We were happy enough with Gaussian approximation of the posterior. There's something that needs to be taken care of there. I'll show you later on. And then the final technical difficulty that maybe some of you caught already is that I'm saying that I'm using 2 surrogate models. One is tuned to the prior, one is tuned to the posterior. Can we do something better than that? This, I have ideas, but I'm not going to show you any results on this. And now details. So let's talk meshes. These are the two meshes that I'm using. It will be either single fidelity. Test 1 is single fidelity. Test 2 is multi-fidelity, but I should say bi-fidelity because we're using only two meshes. So the first mesh is 30K elements, 25 layers, 4 hours for one run here. As I said already, the other one is 250K elements, 6 days to run one example here. Then thermal equation. This is the thermal equation that I'm solving over a time-dependent domain. The thermal equation is nonlinear. You see the CP here term is dependent on T. The K also depends on T. So, as I said, each layer is deposited in one go. We don't simulate the scanning path. It's laid at temperature T activation temperature. Then you wait for it to be cooled, and then you add a new layer. What we don't know is the activation temperature, really, and because that's a non-existing quantity in a way. And then we don't simulate the presence of the powder in the printing room. So what we simulate is just the heat dispersion, the heat exchange with either the powder or the gas that surrounds the part. The part is either drowning in powder or exchanging heat with the air. Where it's not air, it's an inertial inner gas like argon, or I don't remember. And we don't know these two exchange parameters. They are non-existing, so we don't know. We have to tune them. The other two parameters, CP and K, we know them. They are tabulated and linearly interpolated. The elastic equation for computation of the strains is this. There's an elastic part. The Young modulus and the Poisson ratio are temperature dependent. There's a thermal part. The alpha here is also time dependent. And then there's a plastic strain rate computed with the Brand-Royce flow rule, and this is also time dependent, so temperature dependent. So the elastic equation is temperature dependent. And this is all I want to say about the elastic equation. Now, let me go a bit more into the UQ side. So as I said, we assume that we don't know three things: the activation temperature and the two, let's say, heat exchange coefficients. The activation temperature, people in literature use numbers in this range, more or less. The gas diffusion coefficient also is widely unknown. We actually thought that it would be nicer or more convenient to assume uncertainty on the logarithm of the logarithm base 10 of the convection coefficient. So this thing can go between 10 to the minus 5 and 1, essentially. So the logarithm goes between minus 5 and 0. These three uncertain parameters, we take them as uniform. We don't know anything, essentially, more or less. First thing first, I promised you a surrogate model for displacements to do the global sensitivity analysis. The tool that we use is Pascal MATLAB Kit. We build a very coarse isotropic Pascal with 27 points. This is already something, given that one simulation takes 4 days. And then we do a surrogate model for the displacement at these 11 probe points, 1, 2, 3, 4, 5 to 11. And we actually immediately realized that these 3, 11, 10, and 9 were too close to the clamping part. So nothing interesting happens here. We just drop them. Once we have the surrogate model, we convert it into polynomial chaos. We compute the Sobol indices for global sensitivity analysis purposes. And what happens is this. This is the principal Sobol indices, and what happens, you see here that forget about these three. These three are irrelevant. They are reliable. The other 8 probing points, TA and log and the logarithm of the powder, are the only things that matter. So we dropped we fixed, I would say, the third parameter, and from now on we will just consider two uncertain parameters. Next, at this point, we fixed the third parameter to a convenience value, and we refine a bit the surrogate model. This time we have only two parameters, so we can push it a bit further with 25 simulations, 25 simulations using symmetric AI points. And again, here we do a surrogate model for the displacements of 9 probing points, the one label 1 to 5 in the plot, and the one label A, B, C, D, because this is where we have the data by NIST. So we don't care about 6, 7, 8, and 9. Those are, we can forget about them. We only care about 1 to 5 and A to D. This is the surrogate model. You can plot it. It's 2D. It only depends on two parameters. Is it accurate enough? We took the luxury of running 50 random runs and then to check the error, the prediction error of the quantity of the surrogate model. It's not perfect. We were happy enough. Now, this is test case 1. So this is a single fidelity test case, and we're using synthetic data. So synthetic data, now it means that I have to generate the data. So again, I'm generating the data that I'm assuming are the displacements, the work page at the probes 1 to 5 and A to D. So what I do, I fix some values for TA and log of HP. I compute the displacements. I add Gaussian noise with a certain standard deviation. You have here the plot of the values that I'm assuming. So the crosses are the data that I have. And then here it's something perhaps non-standard. So what we do, of course, you write down the negative log likelihood. Everything is fairly standard. And then I want to minimize the negative log likelihood to get the maximum a posteriori. And I do this by Nelder-Mead. It's a derivative-free optimizer. I run it 20 times, starting from different initial conditions. And here something interesting shows up. So the target value is the circle here. And upon doing the minimization, we were sometimes ending in one triangle, sometimes in the other one, sometimes in the third. Now forget about the third for a moment. It's essentially outside the domain, so we don't care. But these two, what's going on here? You see that the computed map is not unique and the isolines are not ellipses, which means that we cannot assume Gaussianity of the posterior. The posterior is just not Gaussian. So what we did a closer inspection. We plotted 1D cuts of the negative log likelihood by fixing either HP, you get this plot, or TA, you get this plot. And these markers here denote where the minima are. And you see that you get essentially one minimum fixing HP, so across TA, and two minima for HP. So what we claim, whether this is appropriate or not, it's up to discussion. I'm happy to talk about this. We made our life easier, and we claimed, okay, the posterior of the TA is Gaussian, the posterior of the log HP is uniform, but on a smaller interval. This is standard. The Gaussianity is standard with it. That's what I'm saying. The posterior of the log HP is uniform on a smaller interval that I'm taking, and we are essentially eyeballing the interval by taking a look at the one-dimensional cut of the NLL. So more or less between -5 and 2, close enough. Okay, so this is what we do. Is this ideal or mathematical rigorous? No, probably, but it worked, let's say, and it doesn't seem completely crazy. Now, the point is that now I have a posterior with well-defined PDFs. So I can generate another surrogate model, this time for the strains, not for the displacements, and this time with one parameter being uniform and the other one being Gaussian. This is the new sampling that I get to build a sparse grid. I again redo my surrogate model. This is how it looks like. This is one surrogate model for one strain at one probe location. We have 120 probe locations. All the green dots here, each of these locations is a location where I'm predicting the strains with the surrogate model. They look like this. Again, we did a comparison of the quality of our surrogate model against 50 random runs, and it seemed to be working even better than before. And now you query with Monte Carlo your surrogate model, and you get the posterior uncertainty that you see here. Now, this is the support of the prior and posterior based quantity of interest. I'm going to show you next the PDFs prior based and posterior based and the target value. So you see here, this is x1.5, so fairly to the right. And then as I'm changing slide, x is increasing, so I'm moving toward the left, so toward the point of maximum warpage. And you see that the concentration is significant, and it's the PDFs are centered where they should, so around the posterior, essentially. So we were happy, essentially. Now, this is it for test case number 1. Now I'm going to move to test number 2. Here, we replace synthetic data with real data and single fidelity with multi-fidelity. What was the issue with the single fidelity? The single fidelity was just incompatible with the real data. The maximum, the range of displacement predicted by the single fidelity mesh was just not enough to cover the real data. So if you want to do inversion on real data, either you use single fidelity on the high mesh or you do multi-fidelity. And remember, one run on the high fidelity takes a week on the ANSYS solvers. So multi-fidelity really is the, as they say, the key enabling technology, right? So now we do an adaptive MISC, so B fidelity in practice, because we're using 17 runs on the coarse mesh and only 5 runs on the high fidelity. This is how the surrogate model for one of the 9 displacement look like. I was skeptical about the fact that this is not monotone increasing. The single fidelity surrogate was monotone increasing. This is not. The engineers were happy, so what can I say? We went along. We had the luxury of having 7 random runs, 7 runs on the high mesh from previous experiments. We were clever enough to store them. So now we have 7 random points to check our surrogate model against. And you see that as the surrogate model goes on, we get a fairly good match, even with this very, say, small number of simulations. So we were happy enough. Now I'm going to the inversion. This time the data that we have, you see here the probes. These are measured by NIST. NIST provides us measurements of the displacements, and they were also able to measure strains. But strains are super complicated and super expensive to measure, so it's not something that happens every day. Again, we replace the surrogate model in the negative likelihood, and we minimize by Nelder-Mead to get a map. And you see that more or less this time the isolines are ellipses for some reason. So this time there's no reason to go weird on the assumptions on the posterior. We claim that the Gaussianity assumption is okay, at least locally. I mean, there's something going on here on the boundary, but the boundary, I don't want to deal with this, let's say. So we're happy enough, let's say, from engineering point of view with the Gaussianity assumption. The problem is, though, that the support of the posterior is not, it overflows the support of the prior. So we are gonna need to run again some other runs, a handful, because if you want now to do a new surrogate, you need to query your model somewhere else. And notice that I cannot use the prior surrogate. I have to use the posterior surrogate because half of the posterior is outside the interval where the prior surrogate model was defined. So really, I need to run something more here. So we did that. At this point, we are really running out of computational budget. So we only have 4 low fidelity points and 1 high fidelity point. This is the maximum that we could afford. We did our surrogate model for the strains based on these 5 plus 1 points, again at 120 points. We actually then found some extra budget to run 2 more high fidelity points, same surrogate. So we were happy enough. Clearly, of course, this time the concentration is smaller because these are real data. And also, one thing that I should have mentioned earlier is that once you compute the map, you can compute a sample estimate of the error at the map. So you sum the misfits between your surrogate model and the actual values at the map. That quantity gives you an estimate of the experimental error. That estimate is completely off. So our surrogate model is not nearly accurate enough, and the physics is not nearly accurate enough to have the same confidence as the experiments. So of course, now we still have some uncertainty in the posterior. But what is very nice, as I was mentioning at the beginning, is that the posterior is again unimodal, and the mode of the posterior, well, I should say the mode of the posterior-based prediction of the quantity of interest fairly well matches with the experimental data. So the colleagues in the engineering department were super happy about this result. So I'm at the end of my talk. I want to just draw some conclusions. Multi-fidelity MISC is a multi-fidelity method. It extends sparse grids. It just add an extra flag, if you want, to each collocation point of a sparse grid. And this flag tells you what mesh you are supposed to run your model on. Here I'm listing the papers that I've been working on MISC. You see that the last ones are fairly recent. We have discussed this challenging engineering application whose bottleneck was really the computational budget. We have 2 papers. The first one is already accepted, and it's on International Journal of Mechanical Sciences, and it's about test 1, so single fidelity surrogate model with synthetic data. The second one was accepted 2 weeks ago on the EJNME journal, and it's multi-fidelity with real data. Everything was done based on the sparse grid MATLAB kit. I take this chance to tell you that finally the paper is out there's a new released last year, 2023 May. There's a paper out there on ACM transaction mathematical software. And we do now have also a GitHub repo for the sparse grid MATLAB kit. So feel free to go there and take a look. One of the many nice features that the latest release has is that the sparse grids MATLAB kit now supports the Ambridge protocol for interfacing the sparse grid MATLAB kit with complex solvers. We didn't use it for these results because we didn't have it back then, but it's a super interesting feature. We do have a paper out on the Ambridge protocol. It's called Democratizing UQ. The first author is Linus Ellinger. There's a lot of people involved. You can go on the archive and take a look. And also on the GitHub of Ambridge, you will see the interface between the sparse grid kit and Ambridge. As I keep saying, sooner or later I will be able to release the MATLAB implementation of MISC. And with this, I am all done. So I thank you for your attention, and I'm happy to take any question. Thanks.
Thank you so much, Lorenzo. So any questions from the audience? Fabio? I don't trust.
Switch on my camera. Hi.
Ciao Lorenzo.
Ciao.
Fabio.
Sì, sì, ti ho visto.
So, if I understood the pipeline of your the workflow that you have followed, so you do computations to build a reduced model,
Yes.
and then you use this reduced model to do the Bayesian inversion.
Yes.
To find a map, or let's say an approximate posterior, upon which you rebuild the reduced model.
Yes.
But for the final UQ step. And when you rebuild the reduced model, you rebuild it completely. So my question is there a way to include the simulations that you have run, the expensive simulations that you have run previously?
To a certain extent, I should say. Well, you can choose to do two things. One thing that you could do, I mean, if the posterior is supported, the support of the posterior is included in the support of the prior, you could, in principle, also just don't rebuild the surrogate model. You just use the same surrogate model to evaluate, and you get samples from the posterior and evaluate those samples on the prior-based surrogate model. The only point is that surrogate is usually, hopefully, the posterior is more concentrated than the prior. So the first surrogate is on a larger domain. So if you want to query it on a small domain, maybe you can get something more accurate, right? If you are willing to rerun a few simulations, you get hopefully a more targeted surrogate model. But in principle, you could just also get away with just using the same surrogate twice. Second, some of the points might be reused, yes. Also, we decided to, there's a technical point, and the technical point is that the posterior is at least partially Gaussian. So this is the sample. This is the sampling strategy for when you have a Gaussian. TA is Gaussian here, and log HP is still uniform. But in principle, you could just forget about the fact that TA is Gaussian. You could assume that TA is uniform just on a smaller support, and then maybe and then build a surrogate model, assuming that the posterior is also prior, and then just use the information on the Gaussianity just when you actually sample the surrogate. If you do that, then even the posterior surrogate model will use the angles of the support. And then the angles might be in common. That's the long story. Third thing, you could, this is research that I'm currently working on, you could try and do a single surrogate that is adaptively it's an adaptive, the adaptive criterion is you have a coarse surrogate. You do a first attempt to do the inversion, see how the posterior looks like, correct the model, correct the surrogate based on the information on the posterior, and go iterative like that. So that's even a more complicated approach. So the answer is, the short answer to your question is, yes, we can reuse at least some of the samples if you do things carefully. We didn't go that far in these works. Did I answer your question?
Yes.
Okay. Any other question from the audience? So Lorenzo, I can add a question here. So if you go to the multi-fidelity part
Yes, here.
So how many did you use? I mean, from the figure you kind of said it, but how many did you use on the higher fidelity versus the low fidelity? And did you consider that they could go higher than 2 levels?
So yes, 17 points on the low fidelity, plus 5 in the first surrogate. So, and then for the second surrogate, it's 5 more, so 22 in total on the low and 6 on the high fidelity. And none of this is in common. So if I had gone down the way that I just talked to with Fabio, then some of these could be in common, but so far they are not in common. Can we use a third mesh? Not a larger one. The larger one is out of discussion. It just takes forever. I mean, I will still be running simulations if I were to wait a month for one simulation. A third mesh that is even coarser than this one. So where is it? Here. Finer than the high fidelity, impossible. Lower than the low fidelity, we tried. They were completely unreliable. And there are geometrical constraints. So as I said, the printing process is simulated by packing together multiple layers. So the physical thing is, I don't know, 4 millimeters. Each layer in practice is like 10 nanometers or whatever. So it has a certain number of layers, and then you group them, but you have to your meshes have to respect the physical layers. So you cannot choose whatever mesh you want. Essentially, you half or twice, let's say. So you see here, this is 50 layers, 25 layers. The next one would be 12 layers of I don't know how many, more or less, and there was not informative. The coarsest one would have been 2 cores, and it would just take us would have us drift apart from the actual results, let's say. So we tried and we couldn't do that.
Okay. Just a comment as well is that on the high fidelity one, in that case study, it almost looks like the result that you have would have been almost equivalent to if you didn't do any a posteriori adaptivity. Right? Because I would have started off at some point that is roughly what the results are.
Well, I mean, perhaps, but my point is let's say no. The uncertainty on the log HP, I don't know. I was told that this was a reasonable range, and then the TA comes from the literature. So yes, the results are not too different, but we do get some. So we're happy about these results, not just because of the shrinking of the concentration of the PDFs, but also because of the fact that after the computation of the map, the map is a good. If you run the solver at the map, you get a decent match with the experimental data, whereas the mode of the quantity of interest computed on the prior interval is the dotted gray line and is unrelated to the NIST data, right? So if you want, of course, it's not super impressive in the concentration of the PDF, but it's the fact that the NIST data are better matched with the posterior interval. It's also interesting and relevant from the application point of view.
I agree. And I can maybe add one small thing. So when you're doing the adaptivity, especially if you would be able to run this longer, let's say you could even possibly do it for case 1. How do you deal with that you have more than a scalar kind of quantity of interest? Because you have here 9 displacements.
Yeah, correct. Yes. Yes. What did we do? Let me think. I don't remember exactly. Michaela was doing the runs, and I don't remember. I should double check, but we were either adapting to only one probe, or we were, so the profit is computed for the MISC. The profit is computed only on one probe, not on 9 of them, or or you take the averages of the 9 probes. So you select the multi-index that gives you the largest improvement in the average of the probes, if that makes sense to you. So you need to somehow...
I mean, it would, like the worst case, or it would be some kind of average, but
yes,
if you want to build this with a very expensive model, you would need to consider something where you don't build single surrogates for each quantity of interest, but you would build them adapted together if they're correlated.
Yes. Also, one thing that I can say is that we tried also to do the inversion having 5 data rather than 9. It doesn't change much because those 9 quantities are actually fairly correlated, because you can't ignore the physics, right? Those 9 quantities are the workbench at these 9 points. And in a way, I mean, when they are sitting on the same piece of metal. So if one goes up, all the other ones go up. And the warping is, okay, it's non-linear, but it's not like a dramatically super large non-linear deformation. So they are pretty much correlated indeed. So we're pretty confident that checking one of them is more or less enough. Michaela was also taking a look at the surrogates, and they all look pretty much the same because of this correlation. So yes. But if you had totally unrelated quantities of interest, then it would be more subtle to figure out, let's say. Yes, absolutely.
Thank you so much. That's what I have. Is there any questions on Zoom? Fabio? Okay, so Fabio, have a question. What is this comb?
Yeah. Again?
So what is this comb? What is this comb? I guess the shape.
The shape? Oh, the shape is super weird. I totally agree. And it's something that has been designed specifically to make the life of the printer as difficult as possible. So you see that there's the teeth of the comb have different thicknesses. Each thickness, the larger the thickness, the easier the diffusion of the heat. So the less it's better when you print it. And then there are angles of these angles are these angles here. They are printing something that goes with this kind of angles requires support structures. So this is also tough for the printer. And also these little details on top, they are also hard to get somehow. So it's not a practical object. It's something, it's a good test case for the printer. I could tell you the name of the printer, but I don't remember. What I remember is the metal is a league of titan and something. So it's not an object that has practical purposes other than giving a hard time to the printer.
Okay, so it's not a comb?
It's not technically a comb, no. No, it's like 5 centimeters or so, yes.
Okay, so thank you so much, Lorenzo, for a nice talk.
Thanks, everyone. Thank you. See you soon. Bye.
Bye. Okay, so we will have a poster session at 5. So I hope many of you can attend. And thank you all for attending.